This is part 4 of section 3.2. We have one more application of logarithms, and it is called Newton's law of cooling. If T of t is the temperature of an object at time t, T sub s is the surrounding temperature, T sub 0 is the value of T of t at time 0, so it's your initial temperature, and K is a positive constant that depends on the object, then the temperature after time t is equal to the surrounding temperature plus the difference between the initial temperature and the surrounding temperature times e to the negative kt, and solved in logarithmic form, it is this. This is basically if you take a cookie sheet out of a 350-degree oven and you set it out in a 72-degree room, how long will it take for it to cool down? It will eventually reach 72 degrees. That's what this is doing. Now that K value depends entirely on what it is that is supposed to be cooling down. Some objects cool faster than others. Okay, so let's just look at this problem. The local McDonald's franchise has discovered that when coffee is poured from a coffee maker whose contents are 180 degrees Fahrenheit into a non-insulated pot, after 1 minute, the coffee cools to 165 degrees Fahrenheit if the room is 72 degrees. How long should the employees wait before pouring the coffee from this non-insulated pot into cups so that they can deliver it to customers at 120 degrees Fahrenheit? Okay, we are first going to have to find the K value, and then we're going to have to use an improved formula to find the time that we're looking for here. So let's just start off here. Our coffee in the very beginning is 180 degrees. So that is my initial temperature. So that is T0, T sub 0, that's 180. Okay. The temperature of the surrounding room is 72. So T sub s is 72. Okay. Now, I'm going to be solving for K first, so I'm going to use the logarithmic form here. What I do know is that after 1 minute, so when T is 1, I get 165. So T of 1 is equal to 165. So I can plug this all in right here to get natural log of 165 minus the surrounding temperature equal to the initial temperature minus the surrounding temperature and this is going to equal negative KT. My T is 1, so this is just K. All right, so to simplify this, we have K is going to be negative natural log of, do the subtraction to get 93 over 108. And you can simplify that fraction. If you reduce that, you get 31 over 36. And that is my exact K value. You don't want to get an approximation for this until the very, very end. So since I need to use that K value to figure out the rest of the problem, I'm going to leave it exactly like this. Okay. Now let's come back up here. What are we asked to do once we know our K value? How long, so we're going to be looking for T, should the employees wait before pouring the coffee to deliver it at 120? So when we waited 1 minute, it was 165, and so we're looking for how many minutes until it gets to 120. So I have natural log of 120 minus 72 over 180 minus 72 is equal to K times T. So t times negative natural log of 31 over 36. Okay, now if you do this arithmetic and you reduce it, you get natural log of 4/9 is equal to negative natural log of 31 over 36, and that's t times that. So divide both sides by this, and your t value is going to be natural log of 4/9. I messed up here. That should be, my problem here is minus k. So this should have an extra minus here, which makes that plus. So because it was minus t and k. So this is divided by positive natural log of 31 over 36. And if you do that arithmetic, you'll find that t is approximately 5.4. So these employees should wait approximately 5.4 minutes.